Section 17.2 Nonhomogeneous linear equations. The general solution of the nonhomogeneous differential equation ay double prime plus by prime plus cy equals g of x can be written as y of x equals yp of x plus yc of x, where yp is a particular solution of this nonhomogeneous differential equation, and yc is the general solution of the complementary equation, where it equals 0. So the complementary equation is the homogeneous version of the non-homogeneous linear equation. Since we know how to solve the homogeneous linear equation, we know how to find solutions to yc, so we can prove this real quick. We verified that if y is any solution of our non-homogeneous linear equation, then y minus yp is a solution of the complementary equation. So what we're going to do is we'll subtract yp from both sides, and then we'll check that y minus yp solves yc. Okay, so then we'll plug in y minus yp into our complementary equation, where it equals 0, and we'll check that it actually makes it equal 0. And it turns out that it does. You can plug in, you distribute your derivatives through, and then you group together all of your terms so that we have our linear equations. And then notice this is supposed to equal g of x. This is supposed to equal g of x because it's a particular solution. So we get that g of x minus g of x is equal to 0. So it turns out, yes, if y is a solution to the if y is the general solution to the non-homogeneous differential equation and yp is a particular one, then we'll end up with g of x minus g of x equals 0, so y minus yp will be a solution of the complementary equation. Okay, but this only shows that if there is a solution, then it must look like y minus yp. It doesn't show that y minus yp will automatically solve this thing. In order to check that, we need to plug that y of x equals yp plus yc back into y to make sure that we actually get g of x in the end. So we do that. We take yp plus yc, we plug that in for y, and again we distribute our derivatives, we group together so that we have our linear equations, and then notice this one is a particular solution to the non-homogeneous differential equation, so that equals g of x. This one is a solution to the complementary equation, which is homogeneous, so it equals 0. So we do get g of x, which is the solution that we want. So we've proven that we can solve non-homogeneous differential equations as long as we know the solution to the complementary equation and a particular solution to the non-homogeneous differential equation, and then we'll get every single solution by combining them. So the way that we'll solve these things is using two different methods. Our first method will be the method of undetermined coefficients. So we take a look at the structure of g of x. If it happens to be an exponential function, either times a polynomial or times a sine or cosine function, then what we'll do is we'll take our particular solution and we'll try to make it a more general version. So if it equals a polynomial of degree n, then we'll make it another polynomial equal to the same degree, but just a more general version with arbitrary coefficients. If it equals a trig function, then we'll have it equal a sum of two different trig functions, cosine and sine, to make it even more general. And then on the off chance that any term of our particular solution, our candidate for a particular solution, or our trial solution, is equal to the solution of the complementary equation, we will multiply it by x or x squared so that it looks a little bit different, so that we actually get a different solution so that we can add it together to get our general solution. So let's do an example of this. Say we want to solve this non-homogeneous linear equation. Notice it equals x squared, not 0. So what we'll do is first we'll look for the complementary equation, which is y double prime plus y prime minus 2y equals 0. It's the homogeneous version. And then we'll look at the auxiliary equation, which is r squared plus r minus 2. Since we already know how to solve these things, we factor out we factor this quadratic, we get r minus 1 times r plus 2, and we're looking for when this thing equals 0. So that's when r is equal to 1, and that's when r is equal to negative 2. So we have two different positive real roots. Well, positive's not so important. Actually, this one's not positive, it's negative. We have two different real roots. So we'll make this r1 and we'll make this r2. And we'll end up with the complementary solution given by c1 times e to the r1x, so that's just e to the x, plus c2 times e to the r2x, so that's just e to the minus 2x. And now we need to see if we can find a particular solution. So notice that g of x is x squared, so that's a polynomial. So that means that we should take our particular solution to be a general quadratic, because this thing's of degree 2. So a general quadratic has the form ax squared plus bx plus c. So we have not determined these coefficients yet, so in order to determine them, how about we take some derivatives? We'll take yp prime, and notice that's equal to 2ax plus b, because a, b, and c are constants. And we'll take the second derivative, yp double prime, and we get 2a. And now what we can do is plug all of this back into our non-homogeneous differential equation. So y double prime will be 2a plus y prime, which is 2ax plus b, minus 2 times y, so that's 2 times ax squared plus bx plus c. And we want this to equal x squared, because that's what we're given. So then what we can do is distribute our negative 2, and we can group together all our x squared terms. It's just negative 2ax squared. Group together our x terms, and we get 2a minus 2b times x, and group together our constant terms, so that's just 2a plus b minus 2c, and this is supposed to equal x squared. So then, if we have a polynomial equal another polynomial, the coefficients must match. So this must be 1 because there's 1x squared on the other side, and since there's no x's, this must be 0. There's no constant term on the other side, this must be 0. So we have minus 2a equals 1. We have 2a minus 2b equals 0. And we have 2a plus b minus 2c equals 0. So the first equation tells us that a is equal to minus 1/2. And then plugging in minus 1/2 for a in the second equation gives us b equal to minus 1/2 also. And then plugging in a and b into the third equation gives us c equal to minus 3/4. So that means that we now know what our particular solution is. Yp is equal to minus 1/2 x squared. Just plugging in for what we said we were going to make it equal to. Now that we know what a, b, and c are, minus 1/2 x minus 3/4. So that means that y, our general solution to our non-homogeneous differential equation, is yc plus yp, which is c1 e to the x plus c2 e to the minus 2x minus 1/2 x squared minus 1/2 x minus 3/4. Let's try solving another one. Let's again look at our complementary equation. So it's y double prime plus 4y equals 0. That means that our auxiliary equation is r squared plus 4 equals 0. And this means that our roots are plus or minus 2i. So we have two complex roots. So that means that our complementary equation solution is c1 times the cosine of 2x because notice there's 0 plus or minus 2i. So e to the alpha x is e to the 0x, which is 1. So c1 cosine 2x plus c2 sine 2x. And we'll have our particular solution given by a more general version of the exponential function that we're given. So we just have to multiply by a constant, a e to the 3x. So that means that when we take our derivative, we get 3ae to the 3x. And that means that when we take a second derivative, we get 9ae to the 3x. So if we want to plug all this stuff back into our original differential equation, we get y double prime as 9ae to the 3x plus 4 times y, so that's 4 times a e to the 3x, which is equal to e to the 3x, because that's the whole point of what we're solving for. And this means that we have 13ae to the 3x when we combine our like terms equal to e to the 3x, and we can divide by 13e to the 3x to see that a must be equal to 1/13. So now that we know what our coefficient is, we have determined it, we have yp of x equal to 1/13 e to the 3x. So we have our general solution given by yc plus yp, so that's going to be c1 cosine 2x plus c2 sine 2x plus 1/13 e to the 3x. Alright, how about we do an example where it equals sine? So again, let's take a look at our particular solution. We'll have a general version of sine, so we'll throw a cosine there. So we'll have a times cosine x plus b times sine x, and we'll see what those coefficients are. We take our derivative, and we see that yp prime must be equal to minus a sine x plus b cosine x. So that means that our second derivative for our particular solution should be minus a cosine x minus b sine x. And we're going to plug this into our differential equation that we're given. So we're going to get minus a cosine x minus b sine x for y double prime plus y prime, which is minus a sine x plus b cosine x. And then we'll subtract off 2y, so that's 2 times a cosine x plus b sine x, and that should equal sine x. Okay, so let's group together our cosine and sine terms. So doing that, we get, let's see, negative 3a plus b times cosine plus negative a minus 3b times sine, and that should equal sine. So if this on the left is going to equal this thing on the right, then that means that we have no cosine on the right, so this must be 0. We have 1 sine on the right, so this must be 1. So we have negative 3a plus b equal to 0, and we have negative a minus 3b equal to 1. If we add 3 times the first equation to the second equation, then we can eliminate b, and we can see that a is equal to negative 1/10. And plugging that in for the equation, we can see that b is equal to negative 3/10. So this means that our particular solution is given by negative 1/10 cosine x minus 3/10 sine x. So we just need our complementary solution, but we already did this in example 1. We had the same equation on the left side, or the same expression on the left side, so the homogeneous version is always just equal to 0, so it has the same complementary solution. So that was just c1 times e to the x plus c2 times e to the minus 2x. So that means that y of x is equal to c1 e to the x plus c2 e to the minus 2x minus, I'll factor out the 1/10, times cosine x plus 3 sine x. How about we try solving one now where we have an exponential function and a cosine function. So what we'll do is we'll first look at our auxiliary equation for our complementary solution. So we have r squared minus 4 by reading off of the coefficients here, and that should be equal 0. So that means that r is equal to plus or minus 2 for our roots. So we have 2 real roots, so that means that our complementary solution is given by c1 e to the 2x plus c2 e to the minus 2x. And now what we can do is take a look at y double prime minus 4y equal to x e to the x. How about we look at that separate from cosine? So if it just equals x e to the x, then that means that our particular solution yp, and how about I call it yp1 for just the first part, because it'd just be for x e to the x. So yp1 should equal some linear function, because this is a polynomial. So the most general polynomial for x is ax plus b. And I need that times e to the x. And I'll take my derivatives so that I can see what the coefficients are for this solution. So we have yp1 prime equal to, by the product rule, ax plus a plus b times e to the x. And again, we do the product rule to get our second derivative. Oops, that should be 1. This should be 2. And this will be ax plus 2a plus b e to the x. So that means that if we plug into our differential equation, we get ax plus 2a plus b times e to the x minus 4 times ax plus b times e to the x should equal x e to the x. So how about we group together all e to the x terms on the left, and we get negative 3ax plus 2a minus 3b times e to the x equal to x e to the x. Notice we have e to the x on both sides. This x has a coefficient of 1, so that means that this must be 1 and this must be 0 in order for it to match. So that means that we have negative 3a equal to 1, and we have 2a minus 3b equal to 0. So that means that a should be negative 1/3 and b should be negative 2/9. So that means that our particular solution yp1 of x is negative 1/3 x minus 2/9 times e to the x. So that's only half of it, though. We still haven't dealt with the cosine, so let's do that now. We'll take our differential equation and now set it equal to cosine. So y double prime minus 4y equals cosine 2x. Then that would imply that our particular solution, in that case, let's call it yp2, should equal some constant. We already used a and b, so how about we use c? So our constant c times cosine 2x plus another constant d times sine 2x. And what we'll do is we will take our derivatives. We only need a second derivative to plug in to y double prime. So if we calculate the second derivative, we just have to have this hop out twice, and then take a minus because it'll change the sign, then change back to cosine. So it'll be minus 4c cosine 2x minus 4d sine 2x when we take our second derivative, minus 4 times y, so that'll be 4 times c cosine 2x plus d sine 2x, and that should equal cosine 2x. So we'll group together our cosines and sines. Minus 4c, so that's minus 8c. So minus 8c cosine 2x minus 8d sine 2x, and that should equal cosine 2x. So notice we have no sines on the other side. We only have cosines. So that means that this coefficient should be 0, and we only have one of these cosine 2x's, so this negative 8c should be equal to 1. So this is 1, negative 8d is 0. So now we know that c is negative 1/8 and d is 0. So that means that our particular solution, yp2, should be negative 1/8 cosine 2x. So now I think we have enough that we can write our solution to the entire equation. What we'll do is we'll use the principle of superposition, which says that we can take yp1 and yp2, add them together. The sum of those particular solutions will be a solution to the sum. And it's not the hardest thing to prove, but we'll just take it for granted. So we have yc plus yp1 plus yp2. So that's c1 e to the 2x plus c2 e to the negative 2x minus 1/3 x plus 2/9 e to the x for yp1 minus 1/8 cosine 2x for yp2. Okay, let's try another trig one. In this case, we have our auxiliary equation given by r squared plus 1 equals 0. So that means that our roots are plus or minus I. So the solution of our complementary equation is c1 cosine x plus c2 sine x. So now we'll take a look at our particular solution. We have ypx equal to a cosine x. Let's see. I'm going to leave a little space. I'm about to show you why. A cosine x plus b sine x. But notice that a and b are constants. c1 and c2 are constants. So this is the same solution as the solution to the complementary equation. So we need to modify it. We'll have to throw in an x. And now it's a different solution. We'll take our derivative so that we can see what these coefficients are. And we get a cosine x minus ax sine x plus b sine x plus bx cosine x. And we take another derivative, and we get negative 2a sine x minus ax cosine x plus 2b cosine x minus bx sine x. So that means that if we want to plug in for y double prime plus y, we'll plug in yp double prime plus yp, and we'll get negative 2a sine x plus 2b cosine x, because notice that ax cosine x cancels with that, the bx sine x cancels with that, so that's all we have left. So this should equal sine x, according to what we were given. So that means that, let's say we've got 1 sine x on the right, so this must be 1. We've got 0 cosine x on the left, so this must be 0. So that means that a must be minus 1/2 and b must be 0. So that means that our particular solution is given by negative 1/2 x cosine x. So we have our general solution given by c1 cosine x plus c2 sine x minus 1/2 x cosine x. So notice that in the event that you have a particular solution that's equal to a complementary one, you just throw in an extra x or an extra x squared if you have to, and you modify it slightly, and then you just proceed. Alright, let's see if we could find the trial solution, yp of x, for this differential equation. So because we have exponential function and cosine, it looks like we should write yp of x equal to e to the 2x times a cosine 3x plus b sine 3x. But if we take a look at our auxiliary equation, r squared minus 4r plus 13 equals 0, then we see that we can use the quadratic formula to get that r is equal to 2 plus or minus 3i, which means that our complementary solution is e to the 2x, because e to the alpha x, times c1 cosine 3x plus c2 sine 3x. So we can see that as before, we have to modify it slightly. We'll take ypx to equal x times this thing. So we'll take it to be x e to the 2x times a cosine 3x plus b sine 3x, and we will disregard the our initial assumption for what the particular solution should be. So you always have to be careful to check your complementary solution and adjust your particular solution, your trial solution, as needed. Now remember that all of those examples we just did were examples of our first method of solving non-homogeneous linear equations, the method of undetermined coefficients. For our next method, suppose we have already solved the homogeneous equation and written the solution as we usually do, c1, y1, c2, y2, where y1 and y2 are literally independent solutions. We replace the constants or parameters c1 and c2 by arbitrary functions u1 and u2. We then look for a particular solution of the non-homogeneous equation of this form, where instead of c1 and c2, we just use u1 of x and u2 of x. So we call this method the variation of parameters because we have varied the parameters to make them functions. So this method works more often than the previous one. It works pretty much every single time, but the previous one is a little bit easier to do. So we tend to use the variation of parameters when the method of undetermined coefficients fails. So let's do an example of that. How about we solve the equation y double prime plus y equals tangent of x, where x goes between 0 and pi over 2. So we'll take a look at our auxiliary equation first. So that's r squared plus 1 equals 0, which gives us roots equal to plus or minus I. So that means that our complementary equation y double prime plus y equals 0 has the solution y of x equal to c1 times sine x plus c2 times cosine x. So this means that we can get a particular solution using the variation of parameters by varying c1 to become a function of x, u1 of x, vary c2 to become another function of x, u2 of x, And then we will take our derivative of this particular solution so that we can see what our functions u1 and u2 should be. So when we take our derivative, we get u1 prime times sine of x plus u2 prime times cosine x plus u1 cosine x minus u2 sine of x. So what we've done here is we've used the product rule twice, and then we group together the terms that have our derivatives in them. Now remember, we're using this yp of x to be a particular solution. We're going to use that to get our general solution, but we don't already need our general solution. We're going to build that up out of yp of x and yc of x. So this means that we can make this a little bit more specific to be easier for us to make our calculations easier. We can choose particular functions, u1 and u2, to make our calculations more convenient because we just need one solution to plug in. So how about we take this entire mess over here and make our functions u1 and u2 such that when we take their derivatives, multiplying by cosine and sine, we get 0. Because u1 and u2 are arbitrary functions anyway, so we can just choose them however we like. So we'll take u1 prime times sine plus u2 prime times cosine, and we'll set that equal to 0. And that'll restrict the number of solutions we can get, but we don't care because we just want to get one solution here. So in general, when you're solving via variation of parameters, what you'll do is you'll take u1 prime times y1 plus u2 prime times y2, and you'll set that equal to 0 to make your calculations easier. This way, we can take our second derivative now, yp double prime, and assuming that this entire thing is 0, we won't have to worry about it. We'll just have to take the derivative of this thing. So again, we have to use the product rule twice, but at least we don't have to do it 4 times. So we get u1 prime times cosine minus u2 prime times sine minus u1 times sine minus u2 times cosine. And all we did was differentiate this because we're setting this equal to 0. So this means that yp double prime plus yp must equal u1 prime times cosine minus u2 prime times sine. We're just plugging back into our differential equation, and that should equal tangent. So to figure out what u1 and u2 are, how about we take this equation over here and multiply it by cosine, and this equation over here and multiply it by sine. And that way we'll have this thing will be minus u2 prime sine cosine. This will be plus u2 prime cosine sine. So these will cancel when we add them together. So when we add together the bottom one multiplied by cosine, the top one multiplied by sine, we get u1 prime times sine squared plus cosine squared equals cosine times tangent. So notice that we have sine squared plus cosine squared is 1. So we have u1 prime equal to cosine times tangent. But cosine times tangent is cosine times sine over cosine. The cosine cancels, we just have sine. So we have u1 prime equals sine. So that means that if we anti-differentiate, we can get u1 is equal to minus cosine when we take the antiderivative. Notice we don't need a value of c for the same reason we're able to set this equal to 0. We're just looking for a particular solution here. We're not looking for the general solution. We're going to build a general out of the particular, so we can just, say c is equal to 0, whatever, it doesn't matter. So plugging this in now, we can figure out what u2 prime is. So notice that if we look in our equation over here, we can see that subtract this thing, and we get that u2 prime is minus u1 prime sine x divided by cosine x, solving for u2 prime. So we'll write that minus sine x over cosine x times u1 prime, and that's the same thing as minus sine squared x over cosine, because we know what u1 prime is, it's sine, and sine squared is 1 minus cosine squared, so I can make this cosine squared minus 1 by incorporating this negative, and then cosine squared divided by cosine is cosine, and 1 over cosine is secant. So that's what u2 prime is. So that means that in order to figure out what u2 is, I'll take the antiderivative. So that'll be sine for cosine, and that'll be the natural log of secant plus tangent for secant. Notice that I don't need the absolute value because we have x between 0 and pi over 2, so that means that secant plus tangent will be positive. So now I need to fill in for my particular solution. So we get minus cosine x sine x plus sine x minus the natural log of secant plus tangent, because I can fill in now that I know what u1 and u2 are, times cosine. And this means that I can simplify this a little bit, because I've got minus cosine sine plus sine cosine, so that'll cancel, and I have minus cosine times the natural log of secant plus tangent. So this gives our general solution as c1 sine x plus c2 cosine x for yc of our complementary equation, and we subtract off our particular solution minus cosine x ln secant plus tangent.